Assalamu alaikum, everyone. So this is our recorded video, video number 1. So I will uh, go through the PowerPoint slides. I have written something in my notebook, and then I took the photo there and then pasted in PowerPoint slides. So let's go there. So this is our recorded lecture 1 on buck converter. So the content for today's presentation, first we will go through this volt second balance equations, and then buck converter, the step down operation. We'll go through the operation, physical realization of the converter, how to choose the appropriate size of the inductor, and how to choose the appropriate size of the capacitor. We'll run some quick simulation in Simulink to see how different parameters influences the performance of the buck converter. And then we'll solve a numerical problem related to buck converter. So certain design issues in buck converter. So we'll do the problem solving, and after that we will simulate the solution in Simulink and to see whether the results are correct or not. Okay, so first, this volt sec balance of an inductor. This is a very important concept. It will be used throughout the course. So as we can see in the figure right, for example, this is a figure of the buck converter. So here we have a inductor L connected here, and the current through this inductor doesn't change instantly. So whenever we are turning on or off a switch, it doesn't change instantly. The current, when we give, when the voltage across the inductor is a step voltage, that means it's a fixed voltage, then the current will be basically, you know that L di by dt is equals to V of L. That means I is the integration of voltage. And by that, what it means is that if we have a fixed voltage like this, so if the voltage across the inductor is somewhat like a fixed value, then for this fixed part, if we do the integration, it will be a slope like this. And if the voltage across the inductor is negative for the next part of the duration, then if we do the integration of this negative constant value, then it will come as a negative slope. So the inductor current will be something like this. It will go up, and then after the duty cycle is finished, after the on time, it will have a negative slope, and like this and this. So this inductor current I of L, there's a mistake, it should be I of L here. So this I of L can be written as sum of two components. One is IL DC, like you can see that there is a constant DC part here. So this is the IL DC, and then there is also a ripple on top of this DC part, which is called ILAC. So if you basically sum these two parts, then you will get this inductor current IL. So that is what is written here. So IL is equals to IL DC plus IL AC. Okay, and then if we do the differentiation of this on the two parts, then it's L di L dt. This is equals to L DIL AC part and the DC part. We know that the DC part differentiation is 0 because this is the fixed value. It's a constant, and the constant the differentiation of constant is 0. So this part is basically 0. And then we have the differentiation of the AC part. So basically the voltage across the inductor comes from the derivative of the AC part of the current that is flowing through the inductor. Or in other way, if we do the manipulations, you end up something like this, that 1 over L integration of VL t dt is equals to integration of DIL AC. Or if you integrate these things for a cycle, this should be for 0 to t. So for the whole cycle, this is also for 0 to t. So this is for the whole cycle. So for the whole cycle, the integration value is 0. So that is what this volt-sec balance equation says, is that the integration of VLT dt is 0 over a whole cycle. Okay, so we will use this concept afterwards. Okay, so now go to the buck converter. So in our previous lectures, what we have seen is that we had a voltage source here, and then there was a switch in the middle, and then we had a load, and then we were switching this on and off, and eventually in the output we had a voltage which was like similar to this, but this is the gate pulse, but the voltage output was similar to this, if you remember our previous lecture. And some of you asked that, okay sir, uh, the voltage is not a fixed value, so how can we get this as a fixed constant value output voltage? Now we will go in detail about this buck converter operation. And so this is the circuit of the buck converter. As you can see, we have a voltage source here, which is the V in. So our task is to step down this V in to a V out. So V out should be less than V in, and V out is the voltage across the load. We have two components here. One is L, the inductor, and another is a capacitor C. And then we have a switch which can basically connect to either position number 1 or position number 2. So the first case, when the switch is connected at position number 1, that means it looks like this, and then basically the voltage across the inductor VL, this can be written as V in minus V out. By VL, I mean that this is the voltage across the inductor VL, which is actually V in minus V out. And in the when it is switched off, then VL is actually minus V naught. So the VL is actually minus V naught when it is switched off. That means it's connected to position number 2. Then the input is no longer connected to the load, rather this inductor will feed the load. We'll see it in the upcoming slides. So we have two equations of VL. One is during on time, so which is V in minus V naught. So this corresponds to on time, or the time when it is on, so for this amount of time. And when it is off, for T off, our inductor voltage is basically minus V naught. So this corresponds to T off, this amount of time. So using the volt-sec equation that we have derived in the previous section, we can write that the voltage across the inductor over the whole period is basically 0. And we can then basically extend the integration from 0 to t in, 0 to t on, and at that time VL is basically V in minus V naught dt plus from t on to t. So if you look at the figure here, so first you are doing the integration, or let me change the color here. So the integration time is first we integrate for 0 to t on. If you look at the green line, and then we integrate it from t on to t off during that time. Okay, so this is the overall integration, and this should be equal to 0. Okay, so if you integrate it, then it's v in minus v naught multiplied by t on. If you do this, it's a very simple integration, minus v out multiplied by t minus t on. T is the overall time, how long it is on. Okay, this should be equals to 0. And if you do the simple manipulation, you end up with the equation where v out is basically duty cycle multiplied by v in. Now this duty cycle d can be varied from 0 to 1. So as you change this duty cycle d from 0 to 1, you have an output voltage which is basically varies with the duty cycle. So that means the output voltage is equal to or less than V in, depending on the value of the D. Now, if you look at the physical realization of the circuit, so how we can build this circuit, how we can replace this switch, the physical circuit, is to have a transistor here and a diode here. So in this condition, we basically give the gate pulse in the transistor. So when we give a positive gate pulse in the transistor, let's say when it is on, and at that time the transistor is connected, so that means the voltage at my mouse point is going to be V in, and the diode will be reversed biased. So this part will be open, and so that means when this switch is closed, that means when it is conducting, you have the diode which is open. So the circuit basically looks like this. And in the second case, when this transistor is open, or when we are giving T off, when there is no gate signal here, that means this transistor is no longer conducting the current. So that means the left part is open and the diode is now forward biased, and the circuit looks like this. Now this inductor L is, as we know, that this inductor has a special property that it changes, it resists the change in the current. So whenever this switch, whenever you are turning off this switch, the current actually continues to flow through the inductor. As a result, as you can see from the wave shapes here, so during the on time, when you are turning it off, inductor current does not instantaneously go to a negative value. Rather, it gradually decreases, and it gradually decreases, and the value gradually lowers down to here. Okay, so it doesn't change instantly. So inductor is not like a resistance, where the resistance, the resistance follows the current. The resistance follows the voltage. Basically, the resistance current follows the voltage. Okay, so the inductor current during this operation, when it is in on, that means the inductor current is charging. That means it's increasing, and this slope, again, the slope of this inductor current is can be defined by basically, we know that the voltage across inductor VL is equals to L di by dt. That means that the inductor current is can be so if I write it here, so we have our V of L, which is equals to L multiplied by di over dt. So this slope is basically VL divided by L. That means the voltage across L divided by L. Now this, during for this on time, VL is actually V in minus V naught, as I showed you in the previous slide. Also, you can see it from here that VL is basically, so this is the voltage across inductor L, which is basically V in minus V out. So the slope of this rising part of the current of the inductor current is basically V in minus V out divided by L. And during the falling time, again, if you look at here, so during the falling time, V L is basically minus V naught. So the slope is going to be minus V naught divided by L. And also this is a negative slope, that means it is falling down. So you can also estimate that it's going to be a negative value for the slope. So this is the inductor current IL. Now, if you look at the current that is flowing through the transistor T, so this is the figure for the switch in the or the current in the transistor T. So this can be written as I of T. This I of T will basically follow the inductor current, or is going to be the same as the inductor current for the time when the switches is on. So that means when the switches is on, at that time your IT will have a current value, and this current value will be the same as the inductor current. And whenever your T or the transistor is off, at that time the current value will be 0 through the transistor. That means it's going to be 0. The diode current, on the other hand, if we I have not drawn here the diode current, but if I draw it here like this, the diode current will, on the other hand, be equal to the inductor current when it is off. So during on time, the diode current is 0 because diode is basically reverse bias, so no current is flowing through the diode. So during off time, diode current is 0. However, during on time, the diode will have a current that will be the same as the inductor current. It will be somewhat like this. So this is our ID, the current flowing through the diode. Okay. So this inductor current IL, as we have seen that it has two part, and one is a DC part and the other is an AC part, as is written here by IL DC, and then there is a delta IL which corresponds to the AC component of the inductor current. Now, as this switching is done at a very high frequency, so this capacitor will basically act like a short circuit, or the impedance across this capacitor will be much lower at high frequency compared to the resistances. So most of this ripple, or this delta IL, will flow through the capacitor. So we can say that the capacitor current will be basically somewhere like this. So this can be written as IC. So this is our capacitor current, which will be actually equal to the delta IL AC. So that means the AC part of the inductor current will be the same as the capacitor current, whereas the DC part of the inductor current will be the current in the resistance. So this actually is following the Kirchhoff's current rule. So the current that is passing through the inductor is splitted into two parts. One is flowing through the capacitor and one is flowing through the resistors. As we know, for the DC part, the DC current doesn't pass through the capacitor. The capacitor is basically blocking the DC part. So the DC component will basically flow through the resistance, whereas this AC part, this fluctuating AC part in the inductor current, will flow through the capacitor. So the capacitor current will look like this, and if we know that the voltage across the capacitor, we know that the current across the capacitor IC is equals to C dV by dt. That means the voltage across the inductor, the voltage across the capacitor should be the integration of the current across the capacitor. So if you integrate it, so this is a line, straight line. So it follows somewhere like y is equals to mx, or something, a constant and x, and if we integrate it, then it will become x square. So the curve of the voltage across the capacitor. So this is the VC, value will look somewhat like this. Okay, so this is also our output voltage, because this is the same as V out. Okay, so and this part is the resistance current. Okay, so this is IR. Now, some of you may have some confusion here. Some of you may say that, well, sir, if there is a ripple here, so in certain conditions, we are seeing that there is an output ripple, and we are assuming that the current is DC in the resistance. So according to that, the output should be a fixed value. The answer is it depends on the value of the capacitance. You will see it in the simulation part that it will depend on the value of the capacitor. So if the value of the capacitor is significantly high enough, then it can store the charges, and in that cases you will have a fixed output, which is going to be the output voltage is going to be fixed. This can be also seen, as I said, this impedance of the capacitor or the reactance of the capacitor, which is basically X of C, which is inversely proportional to our omega C. So as the C value is high increasing, as the C value is going high and high, your impedance is basically going down. So whether you increase the frequency or you increase the size of the capacitor, you will basically reduce this ripple content in the output DC. You will see it in the upcoming slides. Okay, so if we look at the current, so this is basically the graph of the transistor current. So transistor current, we are taking it because this is the current, or I in. So this is the current that is basically leaving V in, or the V, I mean the input DC voltage. Okay, so here you can see that this is basically the same as the inductor current, and the DC part of this inductor current, we call it IL here. So if you look at it here, so this is IL, which is the same as this DC part IL here. Okay, and if you do the average of this input current, then the average value is somewhere like this, which is actually T on divided by T multiplied by IL, because this current, the input current, depends on how much time it is turning on, or the T on time. If the T on time is very small, so the average input current will be very small. On the other hand, if the T on time is comparable with the total time or time period, then this input current will be more or less closer to the output current, or this line will basically go up. Okay, so if you can write then I out divided by I in as the I out, or the output current, is the same as the DC current in the inductor. So you can write IL, and then you can write I in as T on divided by T in, T on divided by T multiplied by IL, and then IL and IL is gone, it's 1 over D. So I output is basically 1 over D multiplied by I in. So you can see that this buck converter, as the voltage is having a step down operation, the current is stepping up, the current is increasing. This is obvious because our power input and power output is more or less similar. Of course, we will have certain losses in the circuit. These losses comes from these stray resistances in the inductor, because these are not ideal. In actual circuits, this inductor will have a stray resistance. These diodes are not ideal. That means there will be a forward voltage drop in the diode around 0.7 volt, and if there is a current flowing through this diode, then this 0.7 volt across the diode multiplied by this current will cause a power dissipation through this diode, which will reduce the output power, as well as this capacitor is also not ideal. So there are some resistances also in the capacitor, which will act as a loss component, as well as the switching losses and the conduction losses in the transistor will contribute to the power losses. So your output power will, of course, in the actual circuit operation will not be ideal. That means the efficiency will not be 100%. All these components in real life will have certain resistances, and these switches will have some switching loss as well. So all these things corresponds to the overall losses in the converter. So the efficiency is not going to be 100%. Typically, for this kind of circuits, efficiency lies in the range of 90 to 95%. Okay. So the next thing is what should be the value of L, or the minimum value of L that is needed for continuous current operation in the inductor. By continuous current operation, what I mean here is basically that your current is inductor current is going up and down like this, and as you can see that the slope of the inductor current, which depends on L value, so the higher the L value, the higher the slope, the lower the slope, or the lower the L value, the higher the slope. There is a minimum value of L for which you will reach, basically you will touch this x-axis. So if I reduce the L value, then I will increase basically the slope. That means, let's say if I reduce the L value like this, and if I further reduce it like this, then it will basically touch this x-axis, and for certain time there will be no current in the inductor. That means that the inductor current will be discontinuous. It will not be continuous. So there should be a minimum value of L, which is called L min, that we need to design to have a continuous inductor current operation. So in this part, we will see what should be the value of this L min. Okay, so for marginally continuous inductor currents, so for the case when the inductor current just marginally touches x-axis, but it is not discontinuous operation yet. So if you increase your L any further, then it will cause the operation to be discontinuous, and at that stage your this is your AC part of the inductor current, or delta IL, and this is the average. This one is IL, the DC part of the inductor current. So the peak of this inductor current, IL max, it will be is equals to IL. So this IL plus this part. So this part is basically, if we use this triangle, so if you use this triangle, then I mean, then the slope here, if you look at this triangle here, then the slope here is minus V naught divided by L, and if you multiply it with the time, which is equals to 1 minus D multiplied by T. So if I go a bit, if I do a bit elaboration here, then you will. So this is our T on time. So this time also can be written as D multiplied by T. So D corresponds to T on divided by T, and if you multiply it with T, then you have only T on time. So this T off time can also be written as 1 minus D. So this is 1 minus duty cycle multiplied by T. So if you multiply this time with the slope, then you will get the H value of the height. And if you make half of it, and if you add it to your DC part, then you will get the IL max, which is basically IL plus half of V out divided by L, because this is the slope, and 1 minus D multiplied by T. Of course, you could have done it using this slope as well, but in that case, you had to use D multiplied by T instead of 1 minus D multiplied by T. Okay. So similarly, you can write what's the value of the IL min, or what's the value of this point, the current in this point, which will be equals to IL minus half of V out divided by L. So you will basically have a negative here. So at the boundary, we know that this IL min will be 0. So if you put a 0 in the IL min equation, okay, and we know that in the buck converter, IL or the inductor current is basically the output current. So the inductor DC current, as I said, the inductor DC current is the same as the output current. So if you go back to your previous slide, you can see that this is the inductor DC current, which is same as basically the output current. Okay, so you can write, or you can replace this V out. Uh, you can replace, or you can replace this IL with I out, and then you can replace this I out with V out divided by R, and you cancel this V out each other and do some simple manipulation and end up with the inductor value, which is equals to R over 2 1 minus D 1 over F. This is the minimum inductor that is required to have a continuous current operation. So your inductor value should be higher than this minimum inductance value that you just derived. The next key thing here is that what should be the value of the capacitor, or what should be the value of the ripple voltage for certain capacitor values. So if you look back here, you can see that this capacitor current is basically the AC component in the inductor current, that is the capacitor current. So we have our IL here, and the AC component of the IL is basically the capacitor current, IC. Okay, so in this IC, this is the amount of charge that is going to be stored in the capacitor this is for the positive part of the current, and the same is going to be negative part of the current. So they are going to, sometimes it's going to be here and sometimes it's going to be there. So this delta Q, on the amount of charge stored during this time, is going to be CdV, because we know that from the formula of the capacitor, C is equals to Q divided by V. So the amount of charge that is stored for a given voltage is the capacitance value. So this equation comes from there. So we know that dq is equals to C dV. Okay, and this is actually the area here. So this is the area that is coming in the triangle, which can be written as half and multiplied by IL divided by 2 multiplied by T by 2. So this is the this is half base multiplied by half into base, and then multiplied by the height. So this is delta IL, so it should be delta IL divided by 2. So your dq is 1 over 8f multiplied by delta IL. So you can write CdV as this, and then you can and then you can replace your delta IL with V out divided by L 1 over D T 1 over V out divided by L 1 minus D multiplied by T. So this comes from here. Okay, this is again it's the same thing. This is your slope. So V out divided by L is your slope, and 1 minus D multiplied by T is the time. So if you multiply this slope with the time, then you get the delta IL, or the peak to peak value of IL. Okay, so you just replace it here and then calculate it, get dV by V naught, which is equals to 1 over 8 F square LC 1 minus D. This is actually your ripple voltage. Okay, so here you can see that we have in the previous slides, or here we calculated the value of the L min, and now for a given value of L min, and if you have a certain C value, then you also know the duty cycle D in your design. Of course, it depends on the requirement of your input and output voltage ratio, so you can calculate the amount of voltage ripple. Or in other way, if you have a certain design criteria for a voltage ripple, let's say if you are told to design a voltage ripple of less than 0.1% variation, then you know this dV by V naught value, and then you have to calculate a certain C value your C value should be higher than the threshold value. So for example, here it says to calculate 0.1% variation. So delta V naught divided by V will basically there is dV by V naught is 0.001, which is equals to this equation. And now you know the switching frequency of the circuit, you know the duty cycle, your L comes from this from here, and then you should calculate the value of C, or the minimum value of C, to achieve this ripple factor. Now we must use a C value which is higher than this C to be sure that you do not exceed, you do not violate this ripple voltage variations. Okay. Next, we will go to one numerical problem to further understand this subject area. So this kind of questions you may expect it in exam, or similar kind of questions you may have it in exam. Okay, so it says that consider a buck converter operating at 50 kilohertz. So you are given the switching frequency. You can see that it's extremely high. It's 50 kilohertz switching frequency, fed by 200 volt DC source. So your input voltage is 200 volt DC source, and delivering output of 48 volt, and your output voltage is 48 volt into a nominal load resistance of 4.8 ohm. So your output resistance, or the load resistance, is 4.8 ohm. The inductor is 364.8 microhenry, and the capacitor value is also given, which is 50 microfarad. And we may have questions like A, B, C, D, E, F. I typically like to give you questions similar to this format, so I will ask a lot of questions like 5 or 6, and then small questions, for each part. So in part number A, it says draw the circuit diagram and label the voltage and currents. So you know the circuit diagram, the buck converter from the previous slides. So then you have to draw the circuit diagram. You have to denote which currents goes to where, which is the voltage, and what's the value of all these components. So this is task number 1. It's very simple. The second task, it says sketch the inductor voltage waveform. So in the second task, your task is to sketch the inductor voltage waveform. So you first get the inductor, the inductor voltage waveform during this on time. Okay, so how you get this on time? So this linked with D value, which is actually, we know that this is a buck converter, so the output voltage, which is 48 volt, that should be D multiplied by the input voltage. So your D value should be output voltage divided by input voltage, or in this case is 0.24. And if you multiply it by the time period, as you know, the frequency of the cycle is 50 kilohertz, and your time period is going to be 20 microsecond. So your on time is basically 4.8 microsecond, and the off time is 20 minus 4.8 microsecond. Okay, so during the on time, the voltage in VL is going to be V in minus V out, which is V in minus V out. I think I made a mistake here. So it's not going to be 15 volt, it's going to be 152 volt. So there's a mistake, I made it here. And during the off time, the VL, or the voltage across the inductor, is basically the negative of the output voltage. So the output voltage is 48 volt, and your negative voltage is basically minus 48 volt. Okay, and in the C part, it says that the sketch inductor, transistor, and diode current waveform. So here you are asked to sketch the inductor current, IL, transistor current, and the diode current. If I say only to sketch it, then you have to sketch only the shape of the current. So as you know that this is the on time, this is the gate pulse on, and this is the off time in the gate. So during on time, IL will be positive slope, so it will rise to IL max, and then when it is off, it will fall down. So you have to be careful about the duty cycle here, at least when you're trying. When you answer it, I should get the impression that you understand the question. So if you are drawing it for 50% duty cycle, then it's a wrong answer. So you should answer keeping in mind the amount of time it is on. It should, I mean, of course, it will not be 100% precise, but it should have the impression that you understand, or you know what you are dealing with. Okay, so that should be your dt should be approximately, in this case, it's approximately is 5 microseconds, so it should be 1/4 of the whole time. Okay, and your transistor current IT, or the current in the transistor, that should be the same as the inductor current, only when your duty cycle is or your gate pulse is on. That means at that time your IT should be the same as IL, and when it is off, your IT is 0. And ID is basically the opposite of IT, because the diode current is 0 when the transistor is on. So during the on time, diode current is going to be 0, and when the transistor is off, at that time the diode is conducting, and the diode current is going to be the same as the inductor current at that time. Okay, so if I only ask you to sketch the inductor and transistor current, then your inductor and transistor, you will only sketch the current. If I say that sketch and find the value of the inductor and the transistor current, then you will have to calculate also what is going to be this IL max, what is going to be the IL mean, what is the value of this IL output current, like this. In this case, for example, IL, or the output current, is going to be your output voltage divided by the output resistance, which is approximately 10 ampere. So this IL, or the DC part of the inductor current, is going to be 10 ampere. And what happens for the AC part of the inductor current? For the AC part of the inductor current, you have to basically integrate your inductor voltage and your inductor voltage. If you integrate your inductor voltage, you can see here that you have a constant DC value here, which is around 152 volt. So if you do the integration here, so it will be 152 T. Okay, so this slope, you can find the value of the slope here, and as well as you can also find the value of the slope here, and the same here. So your IL max is the same at this point, and the minimum value is the same as here. So in part D, you are asked to estimate the average RMS value, average and RMS value of each waveform in part C. So whatever value you are getting at part C, you have to basically calculate the value of the average and the RMS value. Now to find this intersection point, once you know the slope, and also you also know the time here, so this dt, as you know the value of t, as you know the value of t, and you know the slope, so you can easily find the intersection point here. And also you can find the intersection point, I mean, it's going to be the same here. So you know this point, you know the value of IL max as well. So from there, I mean, once you know the once you know the average value, this 10 amp, you know this dt, and then you know this slope, which is minus v naught divided by L. So you know the slope, you know the dt, so you calculate delta IL, or the AC peak to peak value, and from there you can find out what's the IL max and what's the IL mean value. And then basically you know all the points in these wave shapes, and then you are asked to calculate what is the average and the RMS value here. First comes the inductor current. So for the inductor current, your average value in the inductor current, you have to calculate it. So you know that this VL is equals to L di dt. So during on time, this is your V, and this is your basically the on duration time. So this is 0.24 multiplied by 20 microsecond, which is equals to this is your inductance value L, and this is your high value. So this is IL peak to peak. So I just put this from here, it's multiplying with VL. So from here you can calculate IL peak to peak is 2 amp, and you get the average, I mean the DC part of the inductor current IL is equals to 10 amp. So IL max is 11 amp, IL minimum is 9 amp. Okay, so the IL average current is 10 amp basically here. It's approximately 10 amp. You can write it like this. So the transistor average current, we know that the transistor average current basically depends on the duty cycle and the inductor current. So its transistor average current is 0.24 multiplied by 10 amp. So you get this 2.4 amp. Now for transistor RMS value, you can this is another way of calculating the transistor average value using the formula of the average current that you know. So this is another way of solving this 2.4 amp. You can get it like this, and the RMS value is basically the square root of the duty cycle, which is 0.24 multiplied by the RMS current here, so which is 4.9 amp. You can also calculate this RMS value based on the RMS equations that you know. Okay, so this is again valid for the diode currents. So for the diode time, you have to multiply the duty cycle during the off period. So that means 1 minus D, which is 0.76 multiplied by 10. This is the average diode current, and your average RMS current is root over 0.76 multiplied by 10, which is 8.7 amp. This is just for a check. Your RMS current and your RMS diode current and the transistor current should be equal to 10 amp, or the current in the inductor, because in the previous slide, if you see here, the inductor current is basically the sum of transistor current and diode current. Okay, so in part C, it says to calculate the output voltage peak to peak value, so the ripple voltage value here. Now, as we know that this inductor current peak to peak is 2 amp, that means the AC part of the inductor current is the current that is flowing through the IC, or the current flowing through the capacitor. So, and this is basically T over 2. So from here, your IC of T is basically IL of T, or the inductor current, minus the DC part of the inductor current, that is the current that is flowing through the capacitor. So you calculate it like this, and then you find what is the Q value. So your Q value is basically CdV. So you do it here. So your half of the time is T over T here, half of the time, because this is T by 2. So this is half base multiplied by height. So this is not 0.1, this is 1 amp. It's a mistake. Okay, so from here you get the Q is equals to 5 microcoulomb. So your C, or the capacitor value, you know the capacitor value, you know what's the value of Q, and you have to find what's the value of delta V. And your delta V here is 0.1 volt. That means your peak to peak ripple is 0.1 volt in the output. The other way, you may ask to design the capacitor in such a way to get a certain ripple percentage. So if you know the output voltage, you can calculate the percentage of ripple in the output, and based on that, you may have to calculate the capacitor value. Okay. So in the last question, it says, how small can we design the inductor while maintaining the continuous current operation? So we know that the inductor current, the first one is a very shortcut. You can follow the second formula directly to calculate the L mean, and we know that the L mean equation is R over 2 1 minus D multiplied by 1 by F. If you place the values here, then you calculate the minimum inductor value to get the continuous current operation. Okay, so that's it here. and after that we will see the simulation of the circuit. So here we basically drawn the basically constructed the same circuit in Simulink, and here our input voltage is 300. Let's see what's the input voltage. Okay, so we have to go to here and then simulation and go to numerical program. Okay, so our input voltage is 200 volt. So this is the source input voltage, and we are measuring the current that is flowing through the switch or the transistor here. We have a diode here, and then this is the voltage measured across the input voltage, and then we have a measurement of the current that is flowing through the inductor L, and then we have a capacitor here, and the current is measured across the capacitor, and then there is a resistance of the load here, and we are measuring the current in the resistance, and we have a gate pulse that is basically, so if you open the gate pulse, you can see that our period or the time period is 1 over our Fs. Fs value for our example was 50 kilohertz. That means it's 50 to the power 3 is 50 kilo, and our pulse width is 0.24, so it's 24%. Okay, and this is our input voltage 200 volt, and then this is our diode. So here you can specify what's the forward voltage in the diode, 0.8 volt, what's the on resistance in the diode, like so. And then we have our inductor, and this inductance value is 364 microhenry as it comes from the question. Our capacitor value is 50 microfarad, and then our resistance value is 4.8 ohm. Okay, so if we run this simple model, then we can see the output in the scope. Okay, so let's see what's there. So if we zoom in the output for results, so the first one is the gate pulse. Okay, so the first one is the gate pulse. So this is 24% of the time the gate is on, and for the 76% of the time the gate signal is basically off. And if you look at the output voltage, okay, so if you do the simple measurements here in the output voltage, so let's say we are taking this point here, and then we want to measure our V out. So our V out at this point is actually the V out value is basically 4.7 e to the power 10 e to the power 1. That means it's 47.4 volt. So it's not exactly 48 volt. There is certain ripple here. It will be more prominent if I zoom in the output voltage, so you can probably then see what's the ripple content here. It's not so easy to see. Okay, so if you zoom in here, you see that this is not a fixed value. There is a ripple present, so there is an up and down. So this is the amount of ripple that you get. Okay. Yes. And if you look at your other waveforms here, the inductor current, the inductor voltage, all these things. So if you look at it here, so our I in, or the input current, so this is the current in the transistor. So our input current is following this blue line. So the blue line is our inductor current, is following the blue line only for the time when our duty cycle or gate pulse is on, and for the rest is going to be 0. So the YOLO becomes 0, or the transistor current becomes 0. And if you look at the capacitor current, so your capacitor current is basically the ripple part of the inductor current. So it's exactly the same of the ripple part of the inductor current. Okay, and your load current IL is a fixed value. I haven't drawn here the diode current, so the diode current would be the same as the inductor current, but only for the time when it is off. Okay, so this gives you and also if you look at the values, so here the average value of the output current is around 10 amp, and the peak value, as you can see here, is peak to peak value. One is 9 amp and another is close to 11 amp, and this is also what we calculated analytically. And this is just a validation of what you have done by hand. So this simulation tool, I will attach it. I will upload it in the classroom, so you can use it. You can further play with all these different values. For example, if, for instance, if I increase or decrease this switching frequency, what happens to it? Okay, or if I change with this output, if I change with this duty cycle, so instead of 24, if I do it 50% of the duty cycle, then our output voltage should increase. Our output voltage should be 100 volt, close to 100 volts. So if we run it, if we quickly run this simulation, then we can see. Okay, so as you can see here, so this is our output voltage, which is equal to 100 volt in the steady condition. Okay, so let's play with other parameters as well. What happens? So what happens if we change this switching frequency? So if we change this switching frequency before running the simulation, let's estimate what's going to change here. So if you change the switching frequency, the obvious change is going to be the impedances here and here is going to be affected because they are frequency dependent. So your capacitor will, as the frequency is now low, so the impedance here will be higher. So there will, there will be more ripples in the output. That is what I expect. Okay. So let's run and then see what's happens here. Yes, so if you look at the output voltage, then you can see that, okay, there are much more amount of ripple now from the previous cases. Okay, so the same thing is also valid. So now change it to 50. The same thing is also valid if you change the RC value. So if you reduce the value of the RC, you will also see the change in the ripple. So if you reduce the value of the RC and run the simulation, and then you can see that this is the ripple. It's the ripple content, and it's pretty high. So that is what we're learning in this course, that what should be the value of this capacitor. So if you are asked to design a circuit like this, then you should be able to calculate the value of the capacitor to meet your customer need. So for certain load, there are maybe some requirement that your ripple voltage should be like this, and at that time your capacitance value should be chosen in such a way that it meets the requirement. And also your inductor current for continuous operation, you may have to you may have to have a certain inductor current. Now let's reduce. In the last part, it says that if we reduce it by 10 times, then we'll have a marginal continuous conduction current mode, and after, if we reduce it further more, then we'll have a discontinuous operation. Now if we look at the simulation results, then see it here. So if I zoom it, this is our inductor current now, the blue line, and you can see clearly that it's marginally touching our x-axis. So if we increase it furthermore, so if I increase this, if I reduce this furthermore, let's say I'm reducing it to 6.3, and then we can see that it will go into discontinuous operation mode. So our inductor current will not be continuous anymore. So you can see that the inductor, as the inductance value is now low, it cannot hold the current anymore. The higher the inductance, the higher it opposes the change in the current. Okay. So your task is also what value of inductance you should choose so that it doesn't I mean it doesn't go to the discontinuous operation mode. This is important because in real life your load may vary. That means your current may vary here. So your inductance should be chosen in such a way that it can address all different load currents. So it can hold also for the minimum load current and for the maximum load current. So I request you to play with this simulation. I mean, this is a very simple circuit. You can I will give you this circuit in the classroom, so you can basically play with different parameters and then see the impact. Okay, I guess this will be very helpful for you. So this ends our lecture number, recorded lecture number 1. I think I hope this will be helpful, and in the class time we will further discuss on the issues that are not clear to you. Thank you very much for listening. Have a nice day. Allah Hafiz.